So, we will talk about the last module in dynamics of ocean structures, where we are going to talk about the stochastic dynamics part. We will discuss very briefly about the stochastic dynamics as applied to offshore structures. Before that, let us try to introduce what is actually meant by a stochastic process. Why is stochastic process different from a random process, and how comfortably a stochastic process can be chosen for doing dynamic analysis of structures. And then once we understand this, once we relate the necessity of doing a stochastic analysis or stochastic process application for loads applied on offshore structures, then one can easily justify why stochastic dynamics can be successfully applied to analysis of offshore structures. So, we will actually not demonstrate any example or any let us say solution talking about stochastic dynamics as applied to offshore structures, but nevertheless we will talk about some fundamental relationships and some equations and some terminologies as applied to dynamics, which is essentially derived from stochastic process. So, the first question comes in this mind is what is actually meant by a stochastic process. We all know that dynamic analysis can be actually done by two ways. You can carry out dynamic analysis essentially by two ways. One is what we call as a deterministic analysis, which we already know. The prerequisite to carry out deterministic analysis is simple. You must actually know the load time history in a fully prescribed form. So, if you know the load time history in a fully prescribed form, why we are talking about load? Because when you talk about analysis, generally there are two ways. One, if you look at the left hand side and right hand side of equation of motion, left hand side talks about essentially structural characteristics. For example, mass, stiffness, C, they are structural properties. Mass is actually a structural property because mass is second moment of area of the given members. So, one can find out for every given member, one can find sigma x square with sigma a and try to find out the assembly of this, I get the mass matrix. Stiffness matrix actually a functional relationship of the characteristics of the structure itself. It depends upon the form and the boundary condition as well. So, again it is a property related to structures. Of course, damping is derived from M and K, therefore, obviously damping will also be a functional characteristic of structural properties, maybe not only necessarily material, because K is involved with E, L, A and I. Therefore, material characteristics will also play an important role, but nevertheless you see K, M essentially are derived from the form, okay, from the structural form. Therefore, it is important that they form essentially focused on the structural geometry, whereas if you look at the right hand side of equation of motion, essentially this talks about loading characteristic. Of course, in certain classical cases like TLP or spar or even triceratop, we have a dependency of f of t on x, where x is also a factor which is governing the derivation of k, m and c. There is interlinking or what we call coupling between the RHS and LHS, that is only on special kind of structural system. Otherwise, usually the practice is RHS or loading is decoupled from the system. That is generally a case in almost all kind of structural phenomena. But in special cases which are form driven, not function driven, then you will have this dependency or coupling effect of mass K and C dependent on the response itself, and therefore they form some complexities which is very special in certain cases. So, on the other hand, when we talk about the load time history, we are not generally confused with the material characteristic, with the mass characteristics or with the damping situation in a given system, because generally they do not vary with time. Okay. However, loading will definitely vary with time, that is why we do dynamic analysis. If loading is also not varying, then the analysis become either static or worse by worse quasi static analysis. We do not do dynamic analysis at all. Therefore, in the whole context, the right hand side of the equation of motion is strongly dependent or influenced by the time variation. Therefore, we talk about that I want the complete prescribed loading time history to perform a deterministic analysis, that is the reason. The second method by which you can perform dynamic analysis is by considering the statistical properties of the load. Statistical properties means generally first order. For example, let us say mu, that is mean and standard deviation. These are the first order characteristics of any given system. So, if you know the statistical properties of the given load, then obviously the response and the results of the analysis will also be expressed usually in the same manner. Okay. So, if you look at the whole scheme of explaining the method of analysis in dynamic scenario, it is governed only by the load. It is generally not governed by the system. Okay. It is true in dynamic as well as static analysis, and it is also true for higher order analysis like non-linear. For example, pushover analysis, for example P delta effect. All these, if you see the classification of analysis in general in structural generic algorithms, are derived only based on the loading criteria. It is never based on the form or the geometry of the structure at all. Why they wanted to make it? Because once you know the loading criteria history defined, you must be able to apply to any form of the structural system available on earth. So, they want to make it more generic. That is the reason why they do not depend on the form, but of course form derives loading from the right hand side of the equation of motion. So, in both the cases, when we talk about deterministic or stochastic, we are only bothered about how the load history is varying. If you are not able to prescribe the load variation in a time domain as detailed as this case, but you only have the mean and standard deviation of variation on time domain for a given loading, then one can do what we call stochastic analysis. So, there is a very serious question here: how stochastic analysis is different from random process, or why stochastic process is different from a random process. Okay. It is very, I mean, both of them are intricately defined more or less in the same manner. Okay. There is a small catch to call the process as stochastic or to call the process random. Now, many people generally have a basic confusion. The moment we say random analysis or random vibrations or random process, they always think that the variable in the given process is not known. That is what they say. Okay. They say that the variable in the given process is unknown, it can assume any value, therefore it is random. That is actually not the definition. Random, or the term randomness, does not come from the basic request or requirement that the variable can assume any value. The variable actually has a definite value. It actually has a value. You do not know the value, therefore the process is random. Okay. There is a very classical difference here. The value of the variable is definite, it does not change, but it is definite between a large bracket. It can assume any value, it has already assumed a value, the value is fixed. Since you do not know that value, as in the case of vice versa here, you call that process random. Okay. So, you apply a tool by randomly you fix this variable or try to find out the value of this variable in the given scheme. That is why it is called random process. Now, in random process we generally call the results as outcome. Okay. You do a random process, you call the results as outcome. Stochastic analysis is also, or stochastic process also random process, except that the outcome what you refer in random is called realization in stochastic. What does it mean? Stochastic process has got more physical definition compared to random process. Random process has got mathematical definition, whereas stochastic process has got physical definition, because these values are physical realization of the given process. So, that is the difference between a random and a stochastic scheme. So, otherwise both of them will have the same mathematical algorithm to follow. They are also dependent on mean and standard deviation and covariance, etc. Random process also depends on the same algorithms. So, there is a difference, is it is mathematically intrinsic, whereas this is realization of physical intensity. So, this is more or less a realization of a given problem. So, now one can ask me a question, when do we apply a random process, when do we apply a stochastic process? Okay? We can give a classical example. I am talking about, of course please understand in mind, we are talking about both these process or only this process applied to the loading history. We are not talking about this process applied to the left hand side. One can ask me a question, sir, what is that beauty if I apply this stochastic scheme to the left hand side? Very interesting. You take a simple bar subject to axial tension, do a tension test in a UTM, plot the stress strain curve for a given material. You take about 1 million samples, plot stress strain curve. You will obviously see, depending upon the grade, rate of loading, temperature, ambience, humidity, pressure, etc., you will not exactly get the superposition of all the curves identical. There will be some variation. Let us pick up only one point, let us say the yield point, let us say the ultimate load, any one point of interest for us. You try to form a table. The table is nothing but the values of yield point sigma yp, sample 1, sample 2, sample 1 10 power 6. You take a mean. So, therefore, you can still apply a mean and standard deviation of the same scheme on left hand side also, okay, because you are assuming that the Young's modulus is going to be, which is the slope of this curve, is going to be always 2 10 power 5 Newton per mm square, megapascal, 210 megapascal, let us say 200 megapascal MPa. So, you are assuming this value to be fixed, but all the time this value may not be fixed. Okay. So, therefore, you can also correct this, which is also one of the important input for stiffness matrix derivation, which is also an important input for mass, because density will also vary. Similarly, take a piece, keep on weighing it, find out the density, you will keep on varying, you can have. So, all these concepts of first order variation can be also applied to material characteristics which are actually the left hand side of equation of motion, but still we will not call that as realization. So, stochastic process is only applied to the load variation, that is very clear, it is very important, okay, because when I move to fatigue analysis I will talk about the characteristic variation which is also stochastic later, but in general stochastic process is referred only to the variation of load in terms of mean and standard deviation, whereas you can also have material properties also varying with mean and standard deviation. Okay. Now, having said this, let us come to an example of a stochastic process. A classical example in terms of load variation of mean and standard deviation could be a sea surface elevation, which we call at eta of t. A typical sea surface elevation can look like this. Let us say this is time t in seconds, this is eta of t, which gives me the amplitude of variation, and of course this is going to be capital T, which we call record length. So, you pick up a record length and look at the variation. Now, one can immediately see you can associate this as a stochastic process, because easily you can find mean and standard deviation, you can always find out what would be the variation of amplitude from the mean. This process is actually done in wind load analysis, where we convert the process into two, one is called the gust component, other is called the mean component. So, what we do in a given history of wind load, we draw a mean line, we take only the variation respect to the mean line and call that component as a gust component, and the mean component what we do. That is why in wind analysis people generally do quasi static analysis, they do not do dynamic analysis, except that the structure is very flexible and one of the character dimension structure is very less compared to height of the structure. If it is exceeding 5, then people do dynamic analysis, otherwise it is not required. Okay. So, in a given time histories like wind loading, it is also converted in the using this scheme. Therefore, for a sea surface elevation, it is very easy for us to know that I can easily estimate mean and standard deviation. Now, interestingly, one can ask me a question, sir, this sea surface elevation is drawn or is observed at a specific geographic location. Maybe the latitude, the longitude is known to me, but however even in that specific location it is observed at a specific time t equals t1. If the t is equal to t2, it will vary. It means you have infinite number of samples appearing. How will you take the mean? Okay, because samples will change as per t, samples will change as per L1, L2, samples will change throughout the year, samples will change throughout n number of years. So, it is a very complex process, okay, because you will not be able to take a mean so easily in such a manner. Okay. Can we design the system with maximum loading? The design will be foolish because you are interpreting a load which does not occur at all. Can you design a system for the minimum loading? The structure has a probability of failure which is not requested in a design. So, how do we design? Okay, therefore, there is a problem. The input load is very complex in nature, which is undefinable, but we are defining it by using random theories available in the literature. Okay. To avoid this, people moved on to the stochastic dynamics or stochastic process, where people said this process is considered to be an ergodic process. So, they redefined the scheme. Then what is ergodic? So, first let us understand, if I convert or assume or idealize this scheme into an ergodic process, the major advantage is the time history variation. Please understand, this variation of the sea surface elevation in terms of amplitude is only on time scale. Okay. I am not looking at the other scale. What could be the other scale? Other scale could be location, can be period, rainfall, maybe other parameters also there. I am not looking at all of them in the parallel axis. I am looking only one axis where only variation with time. So, I am looking at the time history variation of the variable can be realized if process is assumed to be ergodic. So, the main advantage is realization of this. What is realization? From the given variation of time history of amplitude or wave heights or sea surface elevation, I want to know one specific input data which I will use for my analysis. That is called physical realization. So, to make this, I am now getting into a stochastic process. In randomness, this convergence to realization will not happen. Okay, in stochastic process is going to happen. I will tell you how. So, the process need to remain ergodic. Now, the question comes, what is ergodic process? What is ergodic? A stochastic process is known to be ergodic if its statistical properties initially I am bothered only about mean and standard deviation, but then we will talk about coefficient of variation etc. later. If its statistical properties can be deduced from a single sufficiently long sample of the process. Now, one can ask me a question, how do we physically understand this statement? Now, we already know that stochastic process is dependent on statistical parameters. The foremost fundamental statistical parameter which I am interested is, for a given variation, is mean and standard deviation. We all know how to compute them. Okay? For a given mean is nothing but an average, statistical average, and standard deviation is the variation of any variable with respect to the mean and take a square of that, variance and standard deviation. Very simple arithmetic, we can easily find out this. Nowadays calculators also have this value readily available in a given data if you give the data. So, the first level of statistical property is the mean and standard deviation. I have got infinite number of samples. If I am able to classify one single sample from the infinite series whose mean and standard deviation is same as that of the whole process, hypothetically I can pick up that sample for my analysis, because that sample will become a representative value of the whole scheme. It is not the value of the segment. You understand the point? For example, I have n number of schemes. Okay, I take any specific point t where I try to find out mean and standard deviation of all these, and in this sample one of them has the mean and standard deviation as same as that of the mean and standard deviation of the entire scheme. So, I need not have to do my analysis for the entire scheme, do the analysis only for that sample. Okay. If the sample exists, then that process is called ergodic process. Okay. You will not exactly get that same trace, but closer tolerance. Now, the advantages, the biggest advantage is you can pick up that sufficiently long sample from the process which has the same statistical properties as that of the scheme. Where do you get this? You deduce this, you find out this from the given sample. So, how do you do? For everything you find out sigma and mean, for everything you find, for all at given t you find and pick up which is comparable, pick up that sample. Okay. Then the whole scheme is ergodic, and then the stationary process, if it is ergodic, then my problem is solved, because my f of t is now defined. Though it is random in nature, though it has got stochastic variation along different parameters, but still I am able to pick up one sufficiently long sample from the ensemble, which gives the mean and standard deviation or the statistical characteristics as same as that of all the processes. Okay, then it is called ergodic. So, what is the advantage of being ergodic? Now, what is the advantage if the process remains ergodic? If the process is ergodic, nevertheless whatever sample you pick up, it represents the whole process, not the chosen section. That is important. For example, let us say we have a class of 60, we conduct exam on dynamics of structures. We are trying to work out the mean and standard deviation of the marks obtained by the 60 students. If among the 60, and of course this 60 will have variation if I conduct the exam on every Mondays, every Tuesdays, I mean another parameters there. I find out the variation of every student in terms of mean and standard deviation. If one student matches with my mean and standard deviation of the entire class, so if I want to actually show the performance of the entire class to an external auditor, say I want to express that how my class is good in answering, I will not allow the auditor to ask questions to anybody in the class. I will ask him to ask questions only to that point who is representing the whole process and not the individual section. Okay? Then that process is ergodic. Okay? So, if I am able to generally get an ergodic process assumption, it means actually it is an assumption, but by luck if you see in reality sea surface elevation assumes to remain ergodic. Okay. So, it is advantage that we need not have to bother about the variation, we pick up any one sample. It does not mean that which sample are you picking up, because by ergodic definition any sample present in that scheme of ergodic should represent the same mean and standard deviation as that of the whole process. Okay. So, does not matter what sample you pick up, but it is very clear the sample does not give a self understanding within the section, but it is representative value of the whole process. So, that covers by and large a larger domain of variation which is uncertain in the given described loading, which was not available and described in a classical dynamic analysis. Because all the time we talked about f of t, we never looked into the complication of f of t is so intrinsic in the earlier analysis, but in reality it is true that it is so intrinsic. That is an advantage of being ergodic process. Now the question is, how will you define ergodicity mathematically? How will you define ergodicity mathematically? Ergodicity can be defined by two ways, one by mean, other by covariance. Let us say the constant mean of any process is given by mu x. I will write the symbols very clearly. My handwriting may not be that classical, but I will write the symbols very clearly, okay. That is important, because everybody has some demerit. My handwriting when is write faster is very difficult. In fact, sometimes I am not able to read my own handwriting, but that is a fact. But however, I will have to make up by reading the words before and after. So, what I am actually meaning, mu x actually we know it is an expected value of the variable, that is the mean value by definition. Auto covariance, which is expressed as gamma of x of tau, which is the expected value of x of minus mu x multiplied by x of t plus tau minus mu x. These are two classical equations for finding out mean and autocovariance in statistics. Please understand, the autocovariance actually is dependent on the lag tau, not on t. It means it is not a time average, it is actually an average within the ensemble because here tau is important, okay, it is not t. So, they are called ensemble averages and not time average. The mean and standard deviation of a ergodic process is actually an average of all the ensembles at any specific time. It is not time average, you understand the point, whereas in random scheme it is time average. So, we are converting that slightly in a variation that I want to realize. So, now you will really understand stochastic process become a realization of a physical value. Though there are 100 samples, million samples available, I should be able to pick up one sample which gives me the physical meaning of all the process which I can use for the analysis. So, it is called stochastic process, whereas realization is on the time average, whereas this is not on the time average, it is on the ensemble average. Okay. Now, the process said to be mean ergodic if mu hat of x, which is of that of the process, is 1 over time of 0 to the record length t of x of t dt, which is as same as mu of x at t tends to infinity. Now, this is where the bridging is. Please understand that mean and standard deviations, mean and covariance are ensemble averages, not time average. But if you have a scheme where the time average has the same value as that of the ensemble average, then it is called mean ergodic process. Okay? That is what we want. We want to pick up a process where the time average and ensemble average should reflect more or less the same value. Similarly, if you want to call autocovariance ergodic, if the process is said to be the process is said to be autocovariance ergodic if gamma x of tau hat is a time average of the record length t x of t plus tau minus mu x multiplied by x of t minus mu x, which converges to gamma of x tau when t tends to infinity. Now, a process considered to be ergodic 1 when both the conditions are met. When it is both mean ergodic and autocovariance ergodic, the process said to be an ergodic process. You can also do ergodicity check for a discrete random process. Now, this is a continuous process because I have got the variation of record for the entire domain. I can have discrete values also. Ergodicity can be also checked for discrete random variables. For a discrete process, the mean is said to be ergodic when it is between the sample of variable small n to capital N, the n is a record length, that is time, number of records x of n, which is as same as or converges to mean of x when n tends to infinity. So, one can check ergodicity for a continuous scheme, for a discrete scheme as well. So, this assumption implies a major parameter. The above assumption, above means the ergodicity, implies that. What does it imply to me in my analysis? Statistical information of the process is contained. Statistical information of the process is contained in each single realization of the process. I will ask you a very interesting question. Let us say I have a sea surface elevation random data available to me. At t equals, let us say t1, you have an average available to you in the record. You have such averages available to you for about 100 samples. Amongst this, you have picked up any one signal for an analysis. This is an input data now. This input data is typical to what you have here. Picked up this and do an analysis. If the designer or the auditor or the examiner or the faculty or the colleague wants to know that how are you sure that you have not missed out any other signal which is more vulnerable than this signal, then your design is failed. Okay? If you are able to prove that the statistical characteristic of this realization is a part of the entire scheme, then that question becomes null and void. Okay? So, if you do a stochastic analysis by proving that the process is ergodic in nature, both mean as well as covariance ergodic, then all these uncertainties in terms of accounting for large variation in the ensemble will be null and void. Okay? So, that is an advantage when you do a stochastic dynamics or dynamic analysis using stochastic process for a given scheme, because the right hand side of the loading is very highly uncertain and the process highly random in nature. Okay. To avoid this confusion, people should know that how I can check my ergodicity for a given scheme. We stop here, we will discuss it in the next lecture continues, maybe another 6-7 classes we will have, we will stop here. Any questions here?